Alright, this is a hollow uncharged spherical conducting shell with the inner radius A and the outer radius B. A positive charge plus Q is in the cavity at the center of this sphere. Now we have to find out the charge on each of these surface of the system and also the electric potential at point A, B and C. Fine. To solve this one, we are going to use the Gauss's law. So Gauss's law we can use to solve this question number 1. For that one, we are going to consider a Gaussian surface. So for that one, I choose a different color. Say I choose this is my Gaussian surface. Say this is my Gaussian surface, right? So since I keep a positive charge at the center of this shell, so which is inside is hollow basically, right? I keep it at the center of that surface. So now they ask me to find out the in first question determine the charges on each of these surface. So that means that surface, say this is the surface small a, I consider the charge would be the QA small a, and this is the surface the B, say the charge would be over small b. Every time I have to find out the QA and the QB. Fine. To use that one, to find out that one, we will use the Gauss's law, which is you can write that enclose D in A, D dot EA would be that Q enclose, right? Sum of the Q enclose divided by epsilon naught. This is actually the Gauss's law to find out that electric field. Okay, first, for the first case, say for the surface A, which is the A, QA, then we can write this one E dot dA. So this is, I should write that for surface A, which is that one basically. The what with the enclosed charge? Enclosed charge is going to be the small q plus capital QA, right? So that's why I write down that QA plus small q divided by epsilon naught. That must be going to be equal to the 0, right? Since the electric field inside is 0 for conducting sphere, right? The electric field will be basically the 0 over here. Then we can say this is logic, right? We can write, so this is, or I can say this is also for R is greater than actually that A, because I'm choosing, say this is my Gaussian surface radius, which is small r. Fine, then we can say basically that QA plus small q would be equal to the 0, because epsilon naught cannot be 0. Then I can say that the QA would be the minus q, right? So this is the charge. So that means if I keep a positive charge at the center of this conducting hollow sphere, at this surface there will be a minus q over charge. So this is for the first surface. What about for the second surface? You can write for surface B. Surface B, we can also write down surface B would be basically again the total charge would be, if I consider that 1, it would be QA plus QB, right? That must be also equal to the 0, since shell is neutral, right? Shell is the neutral. Then I can say that QB would be basically minus QA, which is going to be that QA actually the negative A, and the QB is going to be that plus Q, right? They say that the shell is neutral, so that's why the total charge of the shell will be also the 0. So that's why I can say that if I keep a positive charge at the conducting hollow sphere at the center, then the outer surface will be negative. Inner surface will be the negative, and the outer surface will be the positive charge. So if you keep a plus 1 nanocoulomb at the center, inner surface will be the minus 1 nanocoulomb, and the outer surface will be the plus 1 nanocoulomb. Alright, to find out the second part of this portion, they are asking me to find out the electric potential at point A, B and C. To solve this one, we are going to use that idea, which would be that potential is a scalar, right? So before that, we have to use that idea of Gauss's law. So you probably know that. So if you have a, say that sphere, say the radius of this sphere, say that R, and the charge is Q. If it is conducting, then we can say that all the charge will be at the surface, right? Conducting or hollow is the same case. So charges at the surface, so that's why there will be no electric field inside that one. So that's why the potential, say if you consider at that a Gaussian surface, say that Gaussian surface is radius is R, then the electric potential at point, say this is the point P, we know that the electric potential at point P is basically K Q by R, which is that small r is greater than capital R. If you say the electric potential at the surface, V stand for S stand for the surface, this is will be also K Q over capital R. Now this case actually R equal to that capital R, and say V, which is say inside a point actually, say that this is point actually that D, I am choosing the point D. In that case, it's also going to the exactly the at the surface. We already discussed this thing actually in the electric field actually, where R is basically the less than capital R. Since why it is so that basically since the electric field is 0 inside, so that's why whatever the potential at the surface, it will be also the same, right? We draw that curve actually, electric potential versus displacement. Probably if I give you that summary, say this is, if you know that the electric field versus R curve, basically this is actually that at surface, this is actually that R equal to the R. Inside the electric field 0, there is a sharp increase, and that is going to the decrease, right? So this is actually the behavior of electric field for hollow or conducting. Whereas the potential curve was this is capital V electric potential displacement. So this is actually that at the surface it maximum and is going to be 1 over R. This is the formula, and whatever the potential at the surface, it is also going to the remain constant, right? That was the curve. Using that idea, we are going to solve this one. So the electric potential at point A, B and the C. Remember, this electric potential in that point has a contribution all of 3, since its electric potential is scalar. So first I'm going to find out that electric potential, say at point A. Say electric potential at point A. There should be that electric potential contribution by the small q, right? At the center, electric plus electric potential by the, say that QA, which is the charge surface at QA, plus the electric potential provided by the surface QB. That's the sum, right? In every point A, B, and the C. Now you can find out, say that electric potential for the Q, we can write, which would be at a distance, say that R, right? We can consider this one. Basically this is the Q. If I consider, say this is my now small r is the, I'm considering, say this is my right now the Gaussian surface, this one, smaller one. Now since this enclosing charge is the Q, we can consider at the center, then we can say the electric potential, which is actually the outside, right? We can write, say that K Q over R, right? Plus for the QA surface, which is that point, actually the inner surface, right? For this is the charge which is the at the surface the QA, but this point the A, which is inside that sphere, right? For the sphere you can consider the inner surface. This point A is the inside of that one, so that means what would be the potential at over here? It would be also the same for over here for the surface QA. So that's why I can write, say that the minus K, small q is the minus tau in the surface QA, divided by A, right? Because this is actually the radius of that point. Okay, now for that potential for that surface QB, which is for the QB surface, this point A is also inside, right? For that surface QA is also the inside point, so that means whatever the potential at the surface QB, it will be also the same for the point A, because it is the inside point. Then the surface for the QB will be K capital Q, sorry, small q, which is the charge on the surface QB, divided by that potential, which would be the B. So that's why we can write that potential at point A as a whole, the potential at point A will be KQ by R minus KQ by A plus KQ by B, where basically R is, we can write down that condition where R is greater than 0 but less than or equal to the A. So this is actually the at point A. Point, we should write point A. Now for the point B, we could write for point B, what with that electric potential at point B, potential by the small q plus potential by the QA plus potential by the QB, which means that point is the B over here. So fine, then we can write that contribution would be this one. If this is the point B, for this Q1, which is at a distance R, you can write, say I'm going to use the different color, which is basically the outside point. This B point is basically the outside point for the small q, and for this QA is also the outside of that one, right? So which is actually the outside of that surface. For the outside of surface, we know that this is basically the equation. for the outside. For a spherical conducting shell, the electric potential at the outside of the surface is basically kq by r, where small r is greater than radius of that bigger r. Then I can write, so this is electric potential by the small charge which is at the center. It should be the kq by r. Electric potential for the charge at the surface qa, which is negative, minus kq by r, because r is greater than radius of that sphere, which is actually that a, plus, but for this qb, the charge for the qb surface, which is the qb, for the qb, b point is inside that sphere. So that's mean whatever the potential over here, it will be also the same for surface qb, right? So that's why we will write down the potential for the surface qb, kq divided by b, right? Then we can write down. So this is going to be cancel out. This one will be cancel out. Is the same. Then bb would be kq by b. So this is actually that potential at point b. We can write where r is greater than or equal to and less than equal to the b. So this is actually the potential at point b. Fine. What about at point c? At point c, we can write point c. So the potential at point c, the potential by the point charge plus potential by the qa charge at the surface A, plus potential by the surface at the point b, right? The c point is basically the outside for all of these three surfaces, all of these three charges. For this one, it is the outside over here, if you consider for that from the center. For the qa, that is also outside, and for the qb, that is also outside, right? So that's why we can write this one would be basically vc would be k charge at the surface, charge at the center, radius is r, minus k q, which is the charge at the surface qa and radius outside, that's a small r, plus k q, which is the charge positive for the surface qb, divided by r, because it is outside of that radius. We are using again that one if greater than 1. Fine. Now we can cancel out. So this is to be cancel out over here. So this is going to be vc is going to be that kq over r, which is basically the potential at point c. You can write down where r is greater than or equal to the b. That's the case actually. You can find it. Also, you can basically consider at which point would be a higher potential, right? You can also find out from that point, depending on this scenario. You can also find out which point would be the higher potential among the point A, B, and C. Because R is basically greater than that one. You can find out if you compare point B and C. So definitely B is smaller than R. Then you can say that the point B is higher potential with respect to B and C.